Welcome to the second to last section of this entire calculus video. As you can hear from my voice, I'm a little tired today. You might be a little tired today too, but I think that with a little bit of calculus, both of us are going to get all the energy. So 4.7 is really nothing new. And I know I say that sometimes, but it really isn't. It's just kind of combining everything or a bunch of things that we've done before. So we're going to start by optimizing over closed and bounded intervals. And right off the bat, that should bring into mind the extreme value theorem, that if we have a continuous function on a closed and bounded interval, there will be a guaranteed absolute max and absolute minimum. And we already found out how to find that. To find the absolute extrema on a closed and bounded interval for a continuous function, we just see how big the function is at the endpoints of the interval, and then look at the critical points and say, well, what's the biggest? What's the smallest? That's all we're doing here. We're just finding absolute extrema like we did earlier in chapter 4. Now, the difference is this whole section is application problems. Okay, so you're going to have to read some paragraphs. You're going to have to write down information. You're going to have to draw pictures. You're going to have to write equations, think back to related rates. A lot of what we're doing in this section has a similar problem-solving strategy as 4.1. So combine that all together with everything in chapter 3. You're going to be taking a bunch of different derivatives of a bunch of different functions, and you're going to be setting them equal to 0, and you're going to be solving, to find those critical points as well. So that's a lot of stuff that you can write here. I didn't write any of it down, but you could if you'd like. That's kind of what we're doing here, and that's where we're at. It's some fun stuff. A little bit of a final fun fact for you. Ooh, lots of alliteration there. This sort of thing, optimization, is what got me into math in the first place, especially in like high school and college. Setting up these equations and trying to actually optimize something in my life. A lot of times video games, but sometimes not video games in my life as well. So it's cool. It's very interesting material to me. Hopefully it'll be interesting to you. Let's start with example 1. We have a rectangular garden, just like this beautiful image from the book. Oh, although the problem with this beautiful image is, why do they have x be the vertical? That's kind of silly. Usually we have x be the horizontal, but that's fine. We can call it whatever we want. We could call the vertical water buffalo instead of x. That would just take a little longer. So we have a rectangular garden that we're constructing using a rock wall as one side of the garden. So that's the bottom. We have a rock wall. So great. And we're using wire fencing for the other 3 sides. So we're only fencing the 3 sides that you see, the X's and the Y's. The rock wall is already fenced. It's a rock wall, all right? So we only have 100 feet of fencing total that we can use. What dimensions would create a garden of maximum area? What is the maximum area? And make sure to verify that this is a maximum and consider the domain. There's a lot of ways of doing this, and you've done actually a lot of similar problems to everything in this section in pre-calculus probably. Okay, so here's what we do. We're going to start off by writing out what are we trying to find the maximum of. We're trying to maximize the area, right? Find the dimensions that would create a garden of maximum area. And what's the area? Length times width. In this case, the length is y and the width is x. So we can find maximum of functions. We know how to find the maximum of functions, the absolute maximum of a function on our domain. But unfortunately, we haven't talked about functions of multiple variables. We've only talked about functions of a single variable. Although in related rates, we actually did take derivatives with respect to time, but that's not what we're doing here. Nothing's changing here. There is no time variable to talk about, so we want to substitute one of these variables. And in this whole section, if we ever have multiple variables, we'll substitute one out using the methods from pre-calculus. So we have this top thing is what's called a objective function. That's not that important of a term. And then the bottom is going to be what's called a constraint function, which we haven't written down yet. So we're trying to maximize the area function subject to the requirement. What is our requirement here? Our requirement is that we only have 100 feet of fencing. So how does that 100 feet of fencing interact with the x's and the y's? Well, that just means that this length plus this length plus this length has to be less than or equal to 100. And we're just going to say equals because we're trying to make it as big as possible. So let's use all the fencing. So the x plus the y plus the x has to equal 100. Collect like terms to get 2x plus y has to be equal to 100. That's our fencing. And we can use that second equation to substitute, right? We have two equations. Let's use one of these equations to substitute out a variable. Just like when you solved systems of equations, you can solve for x, you can solve for y, it doesn't matter. I'm going to solve for y because it's a little easier to me. Subtract 2x from both sides, and now substitute that into our objective function. Now a is x times y, but y is 100 minus 2x. So just replace the y with 100 minus 2x. And now we have a function of a single variable, and we want the absolute maximum. Let's rewrite this a little bit by distributing the x. 100x minus 2x squared. We want the maximum over our domain. What is our domain here? Well, x is the length. X has to be bigger than 0. Let's include the 0 so it is indeed closed. And what's the biggest x can be? 50 feet. Where did that come from? That's because y has to be at least 0 as well. So the smallest y is, even if y is 0, what's x going to be? X is going to be 50 feet if y is 0. All right, so we're maximizing a function over a domain. At this point, boom, it immediately becomes a 4.3 problem. Finding the absolute or global maximum over a closed interval. So I'll run through that really quickly. We take the derivative with respect to x. We get 100 minus 4x. Also, this is a quadratic function. So if you remembered things from pre-calculus about quadratic functions, you could also find the maximum that way. And in fact, you probably have done this problem before or something similar to it, especially if you took a pre-calculus class here at SPSCC. All right, so A prime is that. The candidates for the maximum, right? Candidates for the global extrema are at the endpoints when x is 0, when x is 50, and at the critical points, which we have to find. Critical points are when the derivative equals 0 or when the derivative is undefined. The derivative is never undefined. This derivative is a linear function. It's defined everywhere. And the derivative equals 0 when 4x equals 100 or when x is equal to 25. So our three candidates are these x values. And it's not a y value that we're curious about. What are we trying to maximize? We're maximizing our function. What's our function? Our function is our area function. So when we're trying to find the maximum, we're trying to find the maximum of this function. You could also use the x times y version of this function, but it's usually easier to just plug in one thing. So let's find the area when x is 0. Area is 0. That's probably not the maximum. Plug in 50. You're also going to get 0 because y will be 0 in that case. So these are not going to be our, these are candidates for our biggest area, but in a physical situation, 0 is probably the smallest area you can get. You plug in 25 and, okay, I can't do that one in my head. Well, I could, but it would take a little longer and I might just mess up. So our function, a of x is equal to 100x minus I don't even remember. 100x minus 2x squared. And what is the area when x is 25? And the answer is 1250. So this is going to be where the maximum occurs. So let's go back to the original problem. I have more room. I don't know why I'm trying to fit this in on this page. I gave myself more room. This is where the absolute maximum is going to be. What is the problem asking? Determine the dimensions. So not just the x component. We found the x component, and our units are in feet. So the dimensions of 25 feet by, what does the y value have to be? Well, y value. Said the y value is 100 minus 2x. The y is going to be 50. Y equals 100 minus 2x. So y equals 50. 25 feet by 50 feet. Great. Determine the dimensions that would create a guardian and maximum area. What is the maximum area? Make sure to verify it's a maximum. We did that. And consider the domain. We did that. Great. So for a largest area of 1,250 feet squared. And again, if you multiplied our x by our y, you should get 1250 feet squared. We've answered the problem. We have found the garden of maximum area with these dimensions. And that's basically what this section's all about. And some of the problems get a little messier. So you can approach the problem the way I approached it in the last example. That's kind of a motivating example. That's where things are coming from. But if you really like, some people really, really like that step-by-step instructional method. And so if you like that, there's one here that I will follow for the next example to kind of model that process if you want to have a more formalized approach to these problems. So we can do them in 6 easy steps. Math professors love saying the word easy, even when it's not true. So let's use that on example 2. An open top box is made from a 24-inch, oh man, can we use feet? 24-inch by 36-inch piece of cardboard. You know what? I'm going to do that anyway. 2 feet by 3 feet. I like smaller numbers. Maybe I'll regret that. Piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side. Okay, I don't know what that means. We'll have to figure that out. What size square should be cut out from each corner to get a box with maximum volume? Well, let's go to the problem-solving method. Introduce all variables. If applicable, draw a figure and label all variables. So let's draw a figure. Let's try to figure out what's going on, and then we're going to make some variables. So we have an open top box. Okay, so let's draw the box, and we'll draw the cardboard that makes the box afterwards. So we have some kind of box. It has an open top. Jason, this is a terrible box. And it's open top, so you actually can see this part. Like this. Okay. And it's made by a 2 feet by 3 foot, and you can use feet or inches as you prefer, piece of cardboard by removing a square from each corner of the box. So all it's saying is that we have a big piece of cardboard and we're removing a square from each piece. Right? Because look, if we remove a square from each corner, if we remove, then we can just fold up the sides, right? Like we can fold up this side and that becomes here and so on. Well, I don't know if it's easy to erase that. So that's what we're doing here. So initially, right, this flat piece right here is 2 feet by 3 feet. Pick your poison, inches or feet. I'm just going to choose inches. So this whole thing is 3 feet. This whole thing is 2 feet. And you can use any units you want as long as they make sense and you label them. All right, so, and then it's asking another question, but we're trying to follow the step-by-step instructions. We've drawn the picture. It told us next, part of step 1, identify variables. Well, we have to make some decisions here. You could have the whole length be X, but really, what is it asking about? It's asking about how big the square should be out of each corner. So if you'd like, and again, it really is up to you, this is what we're actually curious about. How big is this little corner? So you could just call that X instead of labeling the whole big box with X's and Y's. So trying to find the variable, a lot of times it's a good strategy to choose your variables around what the problem is asking. It's asking about how big the square should be. So a lot of times that's a good choice for our variable because that's an unknown. And then there might be another variable that we need to introduce. Don't worry too much about it. If it turns out we need to name something else, we'll name it then. So don't spend too long figuring out whether you've named everything. You can always go back and name something that you've missed. All right, introduce all variables. Maybe we've done that. We've drawn a picture and we've labeled all the variables. If we really want to be super duper precise and great math people, we would say let X be the length of the square cut out to make it really clear. All right, labeling it in the picture is good enough for me, but writing this out on the side, that's really good. That's like smiley face while grading good. All right, step 2, determine which quantity is to be maximized or minimized. So in other words, if you'd like, right, which quantity it is to be maximized or minimized, and for what range. Oh, we're not there yet. I'll write that down. Which quantity is to be maximized or minimized, and what range of values of the other variables. This is essentially asking for a function and the domain, just not getting that formal yet. What are we maxing or minning? And what are the range of our other variables? Okay, so let's see. What size square should be cut out of the volume to cut out of the box to get a box of maximum volume? So we're trying to maximize the volume. Maximize the volume. And it didn't ask for an equation yet, so we won't write one yet if we're using this step-by-step process, or you could jump straight to it. And what is our domain? Well, it's not super obvious what our domain is for X. So obviously X has to be at least 0. Technically, it can't really be 0, but we're assuming it can be 0. What's the biggest X can be? And you might say 2 feet. But remember that we're cutting out this square on both sides. So as this square down here gets bigger, this square up here gets bigger too. So the biggest X can be is actually 1 foot or 12 inches if you're doing this problem in inches. If X is bigger than 1 foot, well, it's not going to work anymore because it's getting bigger on both sides. All right. So that's step 2. And again, if you can't determine it at this time, that's fine. You can do that later. Step 3, write a formula for the quantity to be maximized or minimized in terms of the variables. And sometimes there might be multiple variables, like in the last example. So it's our volume. Our volume in general is length times width times height for a box. And this is not the useful formula that we're going to want to use, but it's a start. Just in general, let's start with any box in general. What's the volume? And now in here, we actually know all of these, right? What is the length at the bottom? Well, it's less than 3 feet because it's 3 feet and we're cutting it out. The length is 3 feet minus this X minus this X. So it's 3 minus X minus X. It's 3 minus 2x. Use the same logic for the width. It's 2 minus 2x. What's the height of the box? Well, remember that we're folding up this corner, or like this side right here. This is what gets folded up to become the right side of the box. So the height is just x. So in this case, our volume equation only has a single variable, but we don't have to use substitution like we did in the last one. We're going to eventually be taking the derivative of this, so it's a good idea to FOIL. Let's FOIL this first one and leave the x kind of by itself for now. Going to give us 6 minus 6x minus 4x plus 4x squared. Collect like terms. 6 minus 10x plus 4x squared. And then we can distribute the x afterwards. The volume equation is a function of x. It's 6x minus 10x squared plus 4x cubed. That was step 3. Step 4, write any equations relating the independent variable in the formula from step 3. Use these equations to write the quantity to be maximized or minimized as a function of one variable. So that's step 4. We're not going to have to do that here. But what step 4 is asking us to do is give us that constraint equation. So really, these things right here, whoa, I don't have the writing on. These right here, these are step 4. We're not going to do it in problem 2 because we already have something. Our objective function is already in a single variable. All right. We don't actually have a constraint function here, a constraint equation. So step 5, identify the domain to be considered. We already got that. This is our domain right here. And then step 6, locate the max or min value of the function from step 4. So again, all this is at this point, this is the hard part. This is the 4.7 part. We're done with the 4.7 part. All that's left is to find the global extrema of this function on this domain. So what are we going to do? We're going to check the endpoints. What is the volume when x is 0? It's going to be 0. What is the volume when x is 1? It's going to be 0. And again, this is our x component, and this is our function, which is the volume. We want the volume to be as big as possible. So the other thing that we consider is any critical points. So take the derivative to find the critical points. It's going to be 6 minus 20x plus 12x squared. Set the derivative equal to 0 because we're looking for critical points, and this is a quadratic. It'll be defined everywhere. And we'll factor out greatest common factor. Factor out a 2. And I'm going to rewrite it as well to have the x squared term first. 6x squared minus 10x plus 3. Doing both. Oh man, this looks annoying to factor. Hopefully it does factor. It might just be faster to use the quadratic formula. You can use the guess and check method. You can use the AC method. I'm going to use the AC method right here because it just looks faster to me. So we need two numbers that multiply to a times c. 6 times 3 is 18. That add to negative 10. So they're going to be opposite. They're going to be the same signs. I don't know. There's nothing. I don't think there is anything. Maybe there is something. We'll use a quadratic formula anyway. X is negative b plus or minus the square root of b squared minus 4ac all over 2a. Simplify this out, you'll get 10 plus or minus the square root of 100 minus 72 all over 12. Split up the fraction and reduce. 10 over 12 is 5/6 plus or minus 1/12 times the square root of 28. And you can simplify that a little bit more to get 5/6 plus or minus. This becomes 4 root 7, the radical. 4 over 12 is 1/3. Root 7 like so. So you didn't have to do this by hand at all. You could have just used a calculator to use the quadratic formula. But we're going to have 5, 6 plus or minus. Let's start with the 5, 6 plus 1/3 times the square root of 7. We also have the minus version. Well, the minus version is giving us a negative value. So this is a physical situation. We just want that positive value of about 1.715. What volume? There is something wrong. There's got to be something wrong. This is not in our domain. We must have made an error somewhere. Our domain is x goes from 0 up to 1. Our volume equation is correct. Length times width times height, 3 by 2. So 3 minus 2x, 2 minus 2x times x. You FOIL it out, you are going to get 6 minus 6x minus 4x is 6 minus 10x plus a 4x squared. That's correct. You get 4x cubed minus 10x squared plus 6x, which is what we have. Take the derivative. Derivative looks good. Factor out a 2. That is going to give you 6x squared minus 10x plus 3. Use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. That's good. 10 over 12 is 5, 6 plus or minus 100 minus 72 is 28. That is, oh, it's 4 times 7. That's 2 root 7. So this is actually a 6 right here. That's what happens when you skip steps and do it in your head, Jason. Bad, bad, bad. All right, so we have this and the minus. So in this case, there is no negative answer. But one of these is still trash. The top one is trash. The x can't be more than a foot, right? We're only looking between 0 feet and 1 feet. If the cutout is that big, we have a serious problem. So we're just going to use the minus 1, which is about 0.392. Which sounds a lot better. And again, if you're using inches, you can multiply this by 12, which we actually probably will do at the end. In fact, let's maybe do it right now. Let's take this, multiply it by 12, about 4.7 inches. Since we're dealing with a small answer, it makes sense to convert it back into inches. You don't have to here. Okay, what is it asking? Oh, we need to verify, make sure that this critical point is the volume. Let's plug it into our volume equation. Our volume equation was V of x equals 6x minus 10x squared plus 4x cubed. Well, what happens when we plug in 5, 6 minus 1, 6 times the square root of 7? We get a volume of about 1.056. Or again, we could convert this to inches if we wanted to. All right. How many cubic feet we have? Fun fact, by the way, be very careful. This is a volume in cubic feet. Converting cubic feet to cubic inches is not as simple as just multiplying by 12. Okay, multiplying 12 changes one of the feet to inches, but you'd have to multiply it by 12 times 12 times 12 because there's 3 feet. Cubic feet is feet times feet times feet. You have to change each one of them. So actually, this number would be pretty big if we did have everything in terms of inches. About 1,800 cubic inches I think saying about 1 cubic foot is a little less precision, but it makes a little bit more sense, I think. Let's make sure we've answered the problem. What size square should be cut out to get a box with a maximum volume? So in this case, it didn't ask for the maximum volume. This is the size of the cutout. Or you could answer in feet. I think answering in inches makes more sense. If in this actual physical situation, you might measure the cardboard with 2 feet by 3 feet, but you would also probably make more sense saying, well, let's cut out 4.7 inches or maybe centimeters. Okay. So, but I would accept the other form of the answer as well. And again, one of the advantages to this problem, like a lot of problems, is you really can find the, really can look at this graphically on Desmos, right? X has to be between 0 and 1 here. What's the absolute maximum of this function between 0 and 1? Right here, 1.056 when x is 0.392, just like we had. Okay, so to get full credit for this section, you will have to do it by hand, but checking your answer with a calculator or Desmos or a graph is all very, very good and highly encouraged. Hope you have now been awakened by optimization. This is the method. We did 2 problems here. The next video is nothing new. It's just 3 more problems for more practice. All right. And then we get into a slightly different kind of problem after that. But this is really most of the entire section. Good luck. You can get started and then watch some more videos as you need them. Bye-bye.